In this video, I want to look at two different integrals that require substitution, but when you take the derivative of the inside, you don't just obviously find that derivative somewhere in your integrand. That you're going to have to do a little bit of algebraic trickery to make it work out nicely. So let's look at this first one. What we have is a clear inside function. Indeed, if I look at this 1 minus x that's raised to this power of 3/2, there's this inside function, the 1 minus x, and there's this outside function to the power of 3/2. So it's very natural that I'm going to assign this inside to be my u. But then if I'm going to allow my u to be equal to 1 minus x, well, what does that make my du? My du is equal to negative dx. And it's pretty close. I do indeed have a dx here, and this dx could be, with a negative sign, my du. But the problem is that I have this extra x that's hanging around the front. So what can I do with that? Now, my strategy here is that I actually do have a formula that has an x in it. Indeed, if we look at this definition of u, which is u is equal to 1 minus x, I can write this as x is going to be equal to 1 minus u, just putting it to the other side. So now this x, which occurs here, I could substitute this in as being 1 minus u. So let's just see how everything works out now. I'm going to say this is the integral. The first x is going to turn into 1 minus u. And then I have a u to the power of 3/2. And finally, I have a positive dx. I really need a minus dx if I want to have a du here. So I'm going to take the extra minus sign out the front, and I'm going to write du. Okay, that's looking pretty decent. Now this is something that I think I can manipulate. I'm going to multiply it out. In other words, this is minus, first of all, the 1 in the u creates u to the power of 3/2. And then I'm going to have a minus u to the 1 times u to the 3/2. In other words, what I'm really subtracting off is u to the power of 5/2. The 3/2 I already have, and the 1 when I multiply by this u. So it's u to the 3/2 times u to the 5/2, and all multiplied by du. These are just powers. I can use the power rule in this case. Okay, first of all, I'm going to take the minus sign. U to the n goes to u to the n plus 1 divided by n plus 1. In this case, it's going to go to u to the power of 5/2 divided out by 5/2, or in other words, multiplied by 2/5. And then minus comes together and becomes a positive. U to the 5/2 goes to u to the 7/2 times 2/7. So 2/7 times u to the 7/2, and finally plus c. Now, we're fairly close to being done, but there's one final line, one that is very important here, because the original integrand was in terms of x, and I've got this answer in terms of u. But we're going to agree that this is going to be satisfied if my final answer is back in terms of x. So that's what I want to do. I've got this u is equal to 1 minus x. I'm going to put this in here, and what am I going to get? It's that this is going to be equal to minus 2/5. And in place of u, I put in the 1 minus x, which was our definition of u, to the 5/2. And then 2/7. And in place of u, I put in 1 minus x to the 7/2. And finally, the all-important plus c. So what we really had in this example was one where we had to do this back substitution, as we call it, where there were other parts of the integrand that didn't work out nicely in the du, but you could use the formula for u to manipulate these other parts, and it still was going to be integrable. Okay, let's see one more example of how this can work out. In this case, I'm going to look at this example number 2 here. Well, what's a good choice of u? We have to think about that first. Well, if I do something on the top, u is the top, then nothing really works out nicely in the denominator. But I have seen a few times integrals of the form where you set the denominator to be the u, and it's going to look a little bit like 1 over u, and we can integrate 1 over u, it would be the natural logarithm. So, while I'm not convinced this is going to be a good approach, I'm going to experiment and see whether setting u equal to x plus 2 might be a good idea. Now, if I do that, my du is fairly straightforward. My du is just going to be dx, but the problem remains again this numerator. We have a numerator, it's got all sorts of x's in it, doesn't cleanly work out as anything to do with du. But I can put my formula for u and I can plug that into the top. So let me see how I can go about doing this. If I've got u is equal to x plus 2, that tells me that x is equal to u minus 2. I can just rearrange the formula. And then that's going to tell me that x squared plus 4, because that's what my numerator truly is, x squared plus 4 is, okay, so it's u minus 2 squared plus 4. And u minus 2 squared plus 4 is going to be equal to u squared minus 4u plus 4, and then minus 4, and that's it. All right, so now that we've figured out all this issue with the u, let's actually go back to the original equation. So I'm going to take this, which was all written in terms of x, and write it all in terms of u. I'm going to say that this is the integral. Well, on the top it is the u squared minus the 4u as we determined. On the bottom, x plus 2, that was just our definition of u. And then finally the dx gets translated by the formula dx equal to du into just a du. So what do I have? I have an integral that is now 100% an integral in terms of u, and we can just go and execute computing this. This is just a relatively straightforward integral. The only real thing to do is a bit of algebra. We've got u's on the top, u's on the bottom. Let's cancel. I'll say that this is the integral of a single u on the top minus just the 4 all du. We can say that this is u squared divided by 2 by the power rule minus 4u plus the all-important plus c. Now, we're almost done, but don't forget, we want it in terms of x. Our original integral is in terms of x. Our final integral should also be in terms of x. And what was u? I've already forgotten. U was defined to be x plus 2. So I can therefore say that this is going to be equal to, instead of u, I will write x plus 2, and then it's the x plus 2 squared divided out by 2, minus 4 times x plus 2. And we could expand if we want, but this is perfectly fine, so I'm going to write it as a plus c, and that is my final answer. So then, if we look at both of these two different examples that we have here, effectively what we were doing was saying, we want to use the quote-unquote obvious u substitution, as in we want u to be whatever the most inside-looking thing is. It was inside the 3/2 in the first example, it was the thing on the bottom in the second, but the problem was when we went to do du, there was other stuff in our integrand, and we had to take these other parts of our integrand and write them in terms of u and hope that by a clever choice of u that what we got was going to be integrable as well, and in both of these examples, that was the case.